So now that we've built up a lot of intuition and understanding of both the Nyquist diagram and its connection to the Bode plot and the root locus, now we're just going to solve this problem using everything that you know. We'd like to determine the closed loop stability based on this open loop transfer function and the fact that it's wrapped with unit feedback. And let's use our tools and our Nyquist criteria in order to determine that closed loop stability. So go ahead and give this a try, and then I'll show you my solution. Okay, so this Nyquist plot is nominally plotted for k is equal to 1. And so what we look at here is we look at our open loop transfer function, and we observe that there is indeed one point, one pole that is an open loop unstable pole. So it's located in the right half plane. And so that means that we will require there to be one counterclockwise encirclement of the point s is equal to -1 for this system to be stable. So let's go ahead and take a look at our Nyquist diagram. So here again, this is for k is equal to 1, and we can see that we're right here at this transitional point with k is equal to 1, because this is indeed the point that we care about encircling. So what we would like to do is consider what happens when this point is shifted. So we scale this down by making k less than 1. That would make s is equal to 1 over here. And so if s is 1 is over here, then we can now calculate the encirclements. And so it's useful in this example to go ahead and show where all the arrows go. So we're going to add arrows just like I've done here. And so what we're going to do is we're going to take that string, remember we talked about that elastic string, and we follow along. So if -1 is over here, right here, outside in this left-hand part, then that means that that string rides along this edge and passes through this point, and notice that it has not encircled -1 at all yet. And so now this continues back and comes back to this point, and we still have not encircled 1 yet. And so now we move along. Again, now we've kind of come up and around and down, and now we come back around in this direction. And so now we're finally encircling this in a clockwise direction. And we still have not quite encircled it yet because we're only at 90 degrees at this point. This is now still at an angle of 90 degrees up here. And so then this comes back down and around. And by the time we finally reach this point, then we finally encircled this one time. And so really, you can imagine the encirclement is happening along this loop. And it's a clockwise encirclement right here. So this other part of the loop doesn't really affect the encirclements for when we've scaled the Nyquist down and the point is outside in this region. So in that case, we have one clockwise encirclement. And so that means that there's -1 counterclockwise encirclements, and so that's not equal to 1, and that leaves our system, our closed loop system, as being unstable. Now, if we were to increase k so that beyond 1, so that now -1 is located inside this smaller region, then what would end up happening is we would again do the same trajectory with our string. We'd fix it here and we'd rotate it around here. So that means we've kind of gone around 180 degrees, and now we've done 270. So now we're all the way around like this at 270 degrees, but then we kind of backtrack and go back to 90. So through 180 and back to 90. So again, this is at 90 degrees. And then we come back down to 180. And now we're back at 180. And now we go from 180 to all the way back around and finally encircle it entirely. So now we've encircled this once. So in this case, it's really this inner loop that leads to one counterclockwise encirclement, and the rest of this trajectory essentially cancels out and does nothing. And so here we have one counterclockwise encirclement, and so that equals P, our number, the number of open loop unstable poles, and that yields a closed loop stable system. So this is an example. We haven't seen one of these yet in our activities, but this is an example where the Nyquist criteria shows that our closed loop system is stable for some values of k, even when we have an unstable open loop system. And so if we were to draw out our root locus, it would look something like this, where we have one pole at the origin, one pole at s is equal to 10, and we have a 0 value right here at -1. And so if you draw out the root locus, what ends up happening is these two poles come together, these two branches come together, separate, and then so by increasing k, you're leading these to this this point of multiplicity. They split, and then eventually they finally reach into the left half plane once k is big enough. So there's an example of increasing k actually leads to stability. And so that's what we're seeing, and that critical value of k is equal to 1, where these points would be on the imaginary axis. And so that's an example of, again, where we can use the Nyquist criteria when there is a open loop unstable pole in our open loop transfer function.